So I need a more specific question about the null hypothesis.
Well, for instance, when we're basing it off Mendelian law,
Okay.
when a p-value is either greater than or less than 0.05, do we say that independent assortment is supported if it's higher than 0.05, or is it rejected?
Okay, so p-value less than 0.05, the null hypothesis is rejected. What does that mean to us?
The alternative hypothesis.
So
That means that, what's the null hypothesis? Another word for that is expectation. Our expectation, I don't know. What do you expect if I flip a coin twice? How many heads and how many tails should I get?
1 and 1. 1 and 1.
1 and 1. Why do you expect that? What's that expectation based on?
One of the
Probability, chance. That's exactly Mendel's laws, is probability. So on average, how many offspring of different genotypes or different phenotypes do you expect? So all of the expected values are based in genetics, at least what we've talked about in class, on Mendel's laws. Practical translation for you. If it's a chi-square test and it's asking about linkage, what would Mendel have predicted if you said these are two genes that control two different traits? They're unlinked. He would say they should assort independently, Mendel's second law. So linkage, the expectation is independent assortment, which equals two genes are unlinked, which equals how far apart are they genetically? 50 centimorgans apart. So that's all the expectation of the null hypothesis for calculating linkage using chi-square. Why is it necessary to do this? To use chi-square analysis together with linkage? So what do you know about linkage? What are the basic rules, basic principles? Genetic distance.
Less than 50.
Oh, less than 50 centimorgans, right, more likely linked. So linked genes are less than 50 centimorgans apart, yeah? 50 centimorgans we don't know. They could be at the opposite ends of a chromosome, or they could be on separate chromosomes. I've said that like 6 times during class. But, go ahead.
That means that they are less likely to recombine.
So the problem is, can anybody come up with a situation with genetic mapping in which you would have unlinked genes, but they show a genetic distance less than 50 centimorgans? So here's a diploid individual, 2 different chromosomes, dihybrid. I'm going to tell you these genes are 40 centimorgans apart, which you would tell me that meant that they were linked, but they're not. So what sort of data would we have to collect to calculate a map distance between these genes of 40 centimorgans?
number of parental cells.
So we've got 4 different haplotypes that can be generated out of recombination from that individual. So if that's an F1 dihybrid, here's the F1 haplotypes of the gametes. So 40 centimorgans.
Well, recombination can happen between different chromosomes, can it?
But there is, so how many, this is independent assortment. This is genes on separate chromosomes. So how many chromosomes that have capital A will go with chromosomes that have capital B? You get 25% of all gametes will have a capital A with a little b, 25% have a capital A with a big B, and 25% and 25%. This is the Punnett square in visual form. When you do a cross between a dihybrid and a tester, that's this Punnett square. The tester gives you only gametes that have little a with little b, and the F1 dihybrid can give you all 4 different combinations in equal frequencies. Little a's with big B's, little a's with little b's. This is the expectation. This is the null hypothesis. If genes are unlinked, they're on separate chromosomes, Mendel says every time you grab a gamete, grabs a chromosome that's got a capital A, that'll happen 50% of the time because there are only 2 different chromosomes that have gene A. So half the gametes are going to have little a, half are going to have big A. Of those that have the big A, 50% of the gametes, half of those, a quarter, will have capital B, and the other quarter will have little b. And that's what this Punnett square represents. So that's recombination. You're getting new combinations, in other words, of alleles. You have some, well, I haven't told you which is parental type and which is recombinant. It's sort of irrelevant for this example. You have some recombinant types and you have some parental types. The point is, they're going to be in even numbers. That's what Mendel would have predicted, a 1-to-1 to 1-to-1 ratio. This Punnett square says that it's 25% of each of those 4 different genotypes get generated. So I just wrote in some actual numbers. So 2. So let's say you observed 8 offspring from this cross. You would expect, null hypothesis, expectation, an equal number to total 8. So you'd expect 2, 2, 2, and 2. So then we come back to the question. What observed values for those 4 different F1 haplotypes would you have to calculate a genetic distance of 40 centimorgans? More recombinant, well,
No.
how do you get 40 centimorgans? It's recombinants over total. So if you want to calculate 40 centimorgans, let's say you observe 10 offspring. Then how many recombinants did you observe if you calculated 40 centimorgans? Well, it's okay. I'm changing to 40 centimorgans. That means that if you looked at 10 offspring, 4 of them were recombinant types, 6 were parental types, 10 total. Is it possible that with this configuration of alleles up here, A's on one chromosome, B's on another chromosome, if you looked at 10 different F2 offspring, you would see something like that? So let's say capital A and capital B and lowercase a and lowercase b are the parental types. You wouldn't know that from this question. I haven't given you the P0 cross. I'm just telling you now those are the parental types. So you observed 3 of each of those and 2 of each of those recombinant types. Right? You'd calculate 4 out of 10 individuals were recombinant. Sum the 2. 2 plus 2 is 4. Divide that by the total, that's 10. That's a genetic distance of 40 centimorgans. So there. Perfectly plausible example for genes that are unlinked, yet you collect data that say that they're 40 centimorgans apart. So then the question is this a significant difference? That's why we have to use the chi-square test. Because we've looked at so few individuals, we've only looked at 10. The question is, stop squeaking your chairs and pay attention for a second, because this is the important part. Blah, 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 blah. The important part, the question is 3, 2, 2, and 3 different one than what you would expect, which in this case is what? So those are observed values. If it totals 10, you'd expect 2.5 which I know is not biologically meaningful because you can't have 2.5 organisms, but we don't round. So there's your observed and your expected values. If you have 10 individuals you've looked at, Punnett square says it should be 25% of each of those 4 different genotypes. So you take 10, divide it by 4, that tells you how many expected. So you've got, this is the question. Is 3 to 2 to 2 to 3 different than 2.5 to 2.5 to 2.5 to 2.5? Intuitively, you say, oh, that's pretty close, but they are different numbers. Then you have to set up the chi-square test and actually calculate, is it a significant difference? We haven't looked at very many offspring, guys. We've looked at 10 individuals. If, as I've drawn up here, they are unlinked, what should the genetic distance be? Easy question. 50. We calculated 40. We've only looked at 10 offspring. What happens if we look at one more offspring and it happens to be a little a, big B? And what happens by chance if we look at one more offspring, we take 12, and it's a big A, little b? Now our observed and expected values exactly match. Now we've looked at 12 offspring, right? Now we observe what we would have expected, an equal number of those 4 different genotypes. So when you look at small numbers of offspring, it's chance. You could have something that looks, you might conclude that it's linked based on genetic distance, could still be unlinked. Yeah. Go ahead.
How do you determine what's the parental and what's the recombinant?
I just told you that.
Okay.
If I was giving you this sort of a question, I would have to tell you, because what do you need to know? This is what I want you to know. How would you figure out the parental and the recombinant types? What information did I not give you? The parent cross. Who was it that was crossed together to produce that F1 dihybrid? Right? So if I don't give you that information, I want you to be critical thinkers and tell me when you don't know something. That's really what I'm testing in this class. I want you to be able to know when you don't have enough information to make a solid argument for coming up with an answer. So if you don't have enough information, it's perfectly fine to say, you have not given us enough information to solve this problem. In this case, yeah, I would have had to tell you the P's and the R's. Normally, you would figure that out for yourself from me telling you something like, let's see, what was the parental types? Capital A's and capital B's. So you tell me, actually, in this cross, given the F1 haplotypes and what I've labeled them as parental and recombinant here, what was the P0 cross? You can figure it out from this data. So what are the parental types? Big A with big B. So that means one of the parents had to be homozygous for those alleles. And the other parental type was little a's with little b's. So that had to be the other parent genotype. That's the only way you get gametes from the parents that have those parental type haplotypes. And by the way, my exact same philosophy, or that exact same philosophy of mine is true for pedigrees. I was telling a few of you in office hours just now that the approach for pedigree analysis is write down the whole list of the pedigrees that, if I ask you what is the transmission pattern, write down the list of all of the transmission patterns we've looked at, and then rule out any that you have data to say this transmission pattern definitely doesn't match the pedigree. Rule out. Don't go through and figure out which one could it be. That takes a lot of time. It's easier to look for patterns that rule out certain types, and you get down maybe you get down to a single pedigree inheritance pattern that matches. In which case you can say, I conclude that this must be the inheritance pattern. But if there are 2 or 3 and you can't decide which is which, that could be a valid answer. There is not always one right answer. So I want you to be able to justify why you've chosen the answer that you did. And that's how I understand how well you understand the material.
I noticed that we don't really see carriers based on like just like study guidance on our own, can they create this?
Like assume.
I do, yeah, so physicians and geneticists don't get carrier information. So we get pedigrees that either somebody's got the phenotype or they don't. So we never know who's carriers. We have to figure it out. That's why you haven't seen any carriers on examples that I've given out, or at least not many. So yes, you will have to try to infer from the data you have in the pedigree whether or not carriers exist. And that's entirely to do with when you're trying to decide is this a dominant or recessive inheritance pattern. If you think it's recessive, then you give yourself the option of saying, well, there might be some carriers. And that's usually when you get into situations where you might tell me there is no one answer. I can't decide. It could be dominant, it could be recessive. I need more information. Bless you. Tis the season. Okay. What's the inheritance pattern? Let's practice this. Hopefully this works. I just made it up.
It's not sex.
Okay. So what are all of the different inheritance patterns? So autosomal dominant, autosomal recessive, X dominant, X recessive, Y cytoplasmic.
So it can't be, no.
No.
An affected, so ruling them out, always start with cytoplasmic and Y-linked. So those are the easy ones. So step one.
Nine.
Okay, if it's not cytoplasmic, that's because an affected mom would pass it to all of her kids.
Right.
Okay, so it's not cytoplasmic.
It's not Y-linked either,
So you're already earning points. It's not Y-linked. Why?
Because the mother on the first right position on the left has it. And
You're both right.
Yeah.
So it's in a father, he's got the Y chromosome, he's going to pass his Y chromosome to his son, who is not affected. Therefore, it's not a gene that's being transmitted on the Y chromosome that causes this phenotype. Plus, females won't have Y-linked traits by definition, because females don't have Y chromosomes. So it's not Y-linked. Okay, those are the easy ones. Usually you can rule those out pretty quickly.
It's not X dominant either because the male on the right, if he was affected, it's only X chromosome that's gone to his kids. And
Right.
it's not a disease.
So this male, he's only got one X chromosome. And if this is a dominant disease, he passes his X to his daughter. Because his daughter's not going to get his Y chromosome because she's a daughter. So she would have to be affected. If this was dominant, she'd get the dominant allele from dad. So it's not X dominant.
X recessive is possible.
Yeah, it is. I'll look it up. Skip a generation.
I don't think it
So let's,
Skip a generation.
so here, yeah, is it dominant or recessive looking?
It looks recessive.
Yeah. No, it's definitely.
Ah.
I see skips a generation.
So normally, yes, okay. So we've got two different pedigrees here, really. They come together into one family in the bottom, in the third generation, but we start out with two distinct families. So on the left side, it's in every generation, up here. Right? It doesn't skip a generation. But on this, in this family, it's present in this generation, it skips there. Okay. So that means could this,
Yeah.
just here, could this be dominant?
No.
Okay, so normally for dominance, we look for it present in every generation. But,
This is the middle.
say that louder.
They only had 2 kids.
They've only got 2 kids. So then, oh, chi-square, maybe. What's the probability that somebody who's got a dominant, let's assume that individual is heterozygous for a dominant mutation, minus being the mutant version. Okay, what's the probability that that individual, that male, by chance, passes his plus chromosome to both of 2 kids? Don't bother doing the chi-square test. It's a pretty good chance that by chance he will pass the plus on to both of his kids. So it could be dominant. By chance, he just might not have passed that minus allele on to any of his 2 kids yet. We could force him to have more kids and see if eventually he does have an affected kid in the next generation. But this alone doesn't let us rule out dominance. Could still be dominant, just don't have enough data. Yeah.
I don't think it's X recessive. Because if it would be X recessive, it means the mom has both X affected, then older sons should have it, and they don't.
Exactly right. So this can't be X recessive because this mom would be
And then like,
minus over minus, X minus over X minus. Or both of her X chromosomes would be affected. This is recessive. She'd have to pass one of those X's to her son, who's XY. And he'd only have 1 X chromosome. His X would carry the recessive allele, and he would be affected. So it can't be X recessive. So we're still trying to figure out dominant versus recessive, but at least now we're just down to autosomes.
Wouldn't dominant mean when close half the offspring is affected by disease?
Okay, in which generation? Sorry, let me label these. Generation 1, generation 2, generation 3. So in the 3rd generation?
Well, if the dad was a carrier, that's possible.
Well, if dad, not carrier, but if this is dominant, dad could be a heterozygote. In which case he'd pass the mutation on to what fraction of his kids? Half, which is exactly what we see. So is it dominant or is it recessive? Or at this point, are you willing to say it could be both and move on to the next question? So if this is recessive, let me change colors. If this is recessive, so dominant there in black for generation 2. If this is recessive, what's this dad's genotype? Homozygous, minus over minus. And if that phenotype gets into the next generation, mom has to be a carrier. That's the only way to get a recessive disease in 2 subsequent generations. One parent's affected, one parent's a carrier or also affected.
But then the dad on number 1 has to be a carrier too.
Ah. So again, all in red there, all likely genotypes if this is recessive.
so all the offspring of the 2nd generation would be carriers.
Indeed. If this is recessive, and we're just ifing, then everybody in that generation would be a carrier or affected. Yeah? Which generation? Yes. If the father of the 2nd generation is showing a recessive disorder, then yes. So I'm going to stop there. I'll answer your question, but stop there and just point out that this is more work than you need to do on Friday to conclude that maybe I can't make a conclusion. Right? Once you've ruled out things that can't happen, that's usually a good place to stop. Unless I'm specifically asking you to do a chi-square test for something. Okay.
I was going to ask if we
you were to see that on the test, could we safely assume that if you don't have something saying that this means carrier, that there are no carriers? Or would you want us to kind of do this and add our own carriers in?
I'd want you to, if you were going to argue that something was recessive, if that's going to be your answer, then I'd want you to have checked to make sure that everybody I would want you to draw carriers in. I want you to show that, yes, there could be carriers and that makes sense given the pedigree pattern. Yeah?
When you're gonna ask us in the exam to do a chi-square for these, would you say like, is it statistically likely or do a chi-square? Like, it's not gonna be like a trick question where we were supposed to do it and we didn't or something?
No. I don't want to waste your time doing chi-square tests that you don't have to do.
What would the null look like for this?
So, what's a null hypothesis for this pedigree? So let's assume, so what's the assumption? You pick it, okay, so let's say we're picking let's say you're going to argue this is dominant. And you want to know just this part of the pedigree. Now, this is kind of this is a bad pedigree for doing a chi-square practice, but we'll do it anyway for practice. Say you've concluded this is dominant. You've got one affected dad, an unaffected mom, and you've got 50% of their kids are affected. The reason this is a bad example is because that's what you would expect for dominance, but we don't know actually, so assume that we don't know anything about what's going on in the upper generations. So we're just going to focus on, let's say I just gave you that pedigree, the one that's circled in the humongous line. So let's say I gave you that pedigree, and you were going to claim that was dominant. What sort of chi-square test would you want to set up? What's the question is, we don't know dad's genotype. That's where you use the chi-square test. If you're unsure about somebody's genotype, you're trying to decide, for example, if this is dominant, dad could be plus or minus as drawn up there, or affected, could be homozygous for the, whoa. Yeah, let me modify there we go. Thank you for pointing that out. This is a better example. Yeah. So, yeah, sorry, you have to redraw it. So you're not going to know if that individual's a carrier. There, I'm satisfied now. Plus over minus or dad. Plus over minus or minus over minus. So just draw, if you're drawing this out, just draw what's in that giant black circle. We don't know dad's genotype. Right, he's affected, so we know he's got at least one minus. But we don't know if it's one minus or two. You look at his kids, and what does that make you think? Might make you think 100% of his kids have the disease. That seems more likely that he's got two minuses, because that guarantees you that all of his kids will be affected. But there's always that nagging possibility in the back of your mind that what if he had a fifth kid and the kid was unaffected? What would that tell us? If I showed you a genotype, pedigree that had that would rule out that he was homozygous, right? Okay, we don't have that data, but that's the question we are thinking is we've only looked at 4 kids. What if there was a fifth? Chi-square test. So we can decide whether it's statistically likely that he's a heterozygote or a homozygote using the chi-square test.
Wouldn't it make more sense to assume he's a heterozygote though?
You want to assume heterozygosity. Write that down. Chi-square test. If you have a question about whether an individual is a homozygote or a heterozygote, make your expectation heterozygote. And maybe the reason for doing that will become apparent. So we've observed affected, unaffected. Let's use 4 affected kids, right? And 0 unaffected. So if you assume the father is a carrier, or not a carrier, heterozygous, you don't have carriers with dominant. Then what's our expected ratio of kids? Right. You'd expect 50-50. So half of his kids would be affected and half not. So we're just asking, if he's a heterozygote, what's the probability that he, by chance, gave his minus allele to all 4 of his kids?
To find the expected, can you just divide the total by the number of categories?
That's basically number of categories. No, it's based on Mendel's law. So it's going to be based on
It's be a 1-to-1-to-1 ratio.
Punnett square. Depends on the cross. Even though we're talking about humans. So the reason that the expected ratio is 50-50, 2 and 2, is because like the chi-square test requires, these columns both have to total the same number. And when you have a heterozygote, it's going to be an equal number of affected versus unaffected kids. Because half of the individuals will get the plus, half will get the minus. The reason that we didn't pick dad's a homozygote as our null hypothesis is, what would that be? So expected if het looks like that. Expected if homozygote looks like what? Which exactly matches our observed values. So doing this test is going to give us a p-value of 0. Because if your observed and your expected values perfectly match, there's no doubt that dad's a homozygote, except that's the question we're asking. So that's why we pick heterozygote, because that gives us a different number of observed and expected values. So after you do the math, observed minus expected squared over expected, for both of those affected and unaffected, what does the math leave us with for a chi-square value? 4, which is a p-value with 1 degree of freedom. It's like 0.09.
No, yeah, 0.909.
0.9.
There we go.
Yeah. So 4 kids, not enough information to distinguish whether or not dad's likely a heterozygote. So the null hypothesis is supported. Our null hypothesis or our expectation was that dad's a het. So we can't rule out that dad's possibly a heterozygote. Any heterozygote, all of you are heterozygous somewhere in your genome. I'm pretty sure, unless there's been a lot of inbreeding. And so if you look in your someday kids or your present kids, right, you'd expect that if you had 4 kids, you could have all 4 kids that have one set of alleles. It wouldn't be non-random. That would be expected. Perfectly fine. Normal. Okay. Only when the p-value is less than 0.05 do you reject the null. And in that case, if you say if you reject the expectation that he's a het, what does that mean? We had 2 choices, het or homozygote. If he's not a het, then you conclude he's a homozygote. Let me boil this down to something that's better to remember for the exam. What's the magic number in terms of number of offspring that you have to have before you're going to get a chi-squared test that's statistically significant? You have to have at least 4 kids 4 offspring from a cross to have any chance of getting any statistically significant information. So if you see a pedigree and it's got 2 parents and 2 kids, or 2 parents and 3 kids, don't bother doing the chi-square test, because you're never going to see a p-value that's less than 0.05. Don't answer the question. No, that's where it's absolutely the right thing to do, is to argue, I can't make a decision, it could be dominant or recessive. So in the previous slide, we ruled out X dominant, X recessive, Y linked, cytoplasmic. Say, we don't have enough information.
So we would argue both cases, or just say that?
You would say that it could be autosomal dominant or autosomal recessive. And you don't have enough information to distinguish between the two. Simple as that. Totally fine. I know that's uncomfortable for a testing situation, but that's what we face as practicing scientists. There is no known answer. And we have to know what we don't know. That's the tough thing about being a scientist, but that's what we're here to try to practice. We get the rule, we do our best, and we have to know our limitations.
Can we do a 3-point mapping?
3-point mapping. Okay, we'll take a step back. What's 2-point mapping? What's the question that we're answering if we do 2-point mapping? Are 2-point, are 2 genes linked? Right, and then we want to know how many centimorgans or map units or recombination fraction. So what's 3-point mapping for?
Relative distance. 3 different genes.
3 genes, and that means that if we've got genes A, B, and C, we need to be calculating 3 different distances, A to B, B to C, and A to C, because that's the only way we're going to figure out what their relative order is. Is it A, B, C, or is it A, C, B, or is it C, A, B? Fortunately for you, there's only 3 different orders for 3 genes that you can have. Those are the 3. So you've got a third of chance of getting the order right by guessing. That's not going to get you any points. So you have to have, for 3-point mapping, we're not actually going to do, good news. Did I do a video on 3-point mapping? Don't bother. This is a freebie. I'm not going to do any classic, because normal 3-point mapping looks something like this. You may remember this from the video. I'm not going to ask you to do this on this exam, maybe the final, but not this exam. You have to have a trihybrid test cross. This is how you map the distance between 3 genes at once. You have a cross that involves all 3 genes. Then you cross that to a tester.
We have 2.
Oh, except those are dots. Sorry?
Will we have at least 2-point mapping?
Yeah, 2-point mapping is fair game. 3-point mapping, I'm never going to ask you to solve something like this during this exam. It takes too much time. So don't worry about anything that looks like this. But before you leave, oh, never mind. It's on the recording for you later. This is the easy way to do 3-point mapping, except it's conceptually difficult. So what geneticists might do instead is do 3 sets of 2-point mapping. You do crosses with A and B, and you do crosses with A and C, and you do crosses with B and C. That's fair game for the exam, because you know how to do 2-point mapping, and all you do then is you calculate if the genetic distance between A and B is 5, and the genetic distance between A and C is, I don't know, somebody say a number. I heard 20 first. Then the genetic distance between B and C, okay, 15. So what's the genetic map? The farthest apart genes are A and C. They're the largest distance apart. So then where's B? Is it on outside or in between? Well, normally it could be both. That was why we have to do 3-point mapping, to figure out where B is. So if A to B is 5 units, then B to C is 15 units, then those genetic distances are additive. That's the concept that, yeah, is totally fair game for this exam. So the use of 3 genetic distances to draw a map, which is 3-point mapping, but not all in one cross involving a trihybrid.
Are you gonna give us the distances like that, or are we going to have to calculate?
I could ask you to calculate them, and that's what, if you practice anything, right, focus on transcription and translation. We've done a lot of that recently, so going back in time, focus on how to calculate genetic distances using data that looked something like this. Right, where we started this process, actually. So if you have this sort of a P0 cross, that generates a dihybrid. And you test cross the dihybrid. Then you're going to get a bunch of different genotypes, so that's P0 generation F1. You get the usual 4 different genotypes of F2s. And then I will tell you, these are the number of F2 genotypes you observed, and you figure out which are the parental types, which are the recombinant types, and you calculate the map distance. So let's see. Should I be mean? No, I won't be mean. Not now. This is not the right time. Let's see. Trying to do math in my head, it hurts. Hopefully that works. So what's the genetic distance between genes A and B? So the parental types, capital A with capital B, that's the gamete produced by that P0 and the lowercase letters. So that's a parental type, and capital A with capital B is a parental type. So we have 24 recombinants out of, did I make it total 100? Good. Make the math easy. 24 centimorgans. And if you were going to do, if I was going to put a 3-point map question on this exam, I would make you do that for that cross, which is genes A and B, and there would be a separate cross for genes B and C. There'd be a third cross for gene pair A and C. You calculate 3 different genetic distances.